So in the last lecture, we have derived TCCA, TICA, and time autoencoders based on the idea of minimizing the reconstruction error in time. So we take a model that takes as an input xt, so the state of the system at time t, and makes a prediction for xt plus tau, so the state of the system at a later time, and we compare that to the actual value of the state at that time series, and we compute the prediction error of the model. And we're trying to minimize that over the parameters of the model. And the model could be either linear, as in the case of TCCA or TICA, and it could be nonlinear, as in time autoencoders, where we have neural networks for encoding and decoding the time propagation. Now, in this lecture, we want to compare minimizing the reconstruction error to maximizing time scales or maximizing slowness in some sense, because this is the idea with which we started the lecture. We wanted to find the manifold, a low-dimensional manifold, in which a time series describes the slow motions or the rare events. So we need to explain that or why minimizing the time propagation error actually achieves that. Okay, and we start with TCCA, so time-lagged canonical covariance analysis. And here we simply borrow the properties from canonical covariance analysis that are well known. Let us start with a single latent space vector. So we use TCCA in order to encode the time series into a one-dimensional signal and then decode back to the original time series dimension. Then TCCA finds a single pair of vectors u and v tilde, which are maximally correlated under the correlation matrices or the covariance matrices of the data. So we find the vectors u and v that maximize the autocorrelation or the Rayleigh quotient that is given here. And since y is simply the time-lagged version of x, that means we are looking for the pair of vectors u and v that are maximally correlated in time. Now for multidimensional latent spaces, we have multiple vectors u and v, and we can generalize that concept. We still can show that canonical correlation analysis maximizes the correlation between these vectors, but we have to use a more general concept of correlation. And we do that by maximizing the sum over all pairs of UV vectors. And we can show that this is equivalent to maximizing one of these matrix norms, the trace norm or the Frobenius norm of these normalized covariance matrices of the latent space vectors. And down here you simply find the definition of these trace and Frobenius norms. Those are simply the sums of the singular values or the singular values squared. Now, before dwelling further on this result, we will look at the special case of TCCA named TICA. So this is again just TCCA with time reversibility or with detailed balance. So if the dynamics are symmetric in time, so that means the covariance matrices are symmetric. So the time forward covariance matrix is equal to the time backward covariance matrix. Then TCCA turns into TICA, and instead of a singular value decomposition, we can perform an eigenvalue decomposition in order to derive the results. And in this case, instead of two vectors u and v, or a pair of vectors u and v, we only have a single vector u. And TICA finds the vector u, so the latent space vector u, that if we project our data on it, maximizes the time autocorrelation. And that is very easy to understand now. So that means we take our multidimensional or high-dimensional time series, we find a vector u, we project the data onto this vector. So we compute the scalar product of every single state xt in time with that vector, and then we get a one-dimensional time series. And if we compute the autocorrelation function of that one-dimensional time series, then the value of this autocorrelation function at lag time tau will be maximal over all possible vectors u. So in other words, TICA finds the vector such that the projection on this vector gives the slowest result, or the most autocorrelated result at the chosen lag time tau. But as we have seen before, TICA is also minimizing the prediction error of a linear encoder and decoder matrix. Prediction error in time. So minimizing the prediction error in time and maximizing the time autocorrelation is the same. We can again generalize this to multiple vectors, so multidimensional latent spaces, and we achieve the same result as before for TCCA, just that we only have u vectors instead of u and v vectors here, so the result is just simpler. And we have a few more interesting properties. So for example, if we take our latent space time series and write it into a matrix C, and we compute the covariance matrix C transpose C, again I'm neglecting normalization constants for simplicity here, sorry for that. And we just insert the definition of how C was computed. Then we find this is identical to u tilde transposed u tilde, which is simply this eigenvector matrix of resulting from TICA. And because u tilde was an orthogonal matrix, importantly u tilde is, u is not, but u tilde is an orthogonal matrix, u tilde transposed u tilde is identity, and that means the TICA components are white. The autocorrelation, the covariance matrix between TICA components is an identity matrix, so they are already whitened. Okay, so this was the instantaneous correlation or covariance matrix of the latent space signal. Now we consider the time-lagged covariance matrix of the latent space signal. So we essentially do the same computation, but here instead of 2 times x, we use x and y. So we compute the time-lagged covariance matrix of the latent space coordinates. And when you work that out, you will see this is again a diagonal matrix, and it simply contains the eigenvalues of the eigenvalue decomposition done in TICA. And this is the eigenvalue matrix of the transition matrix between the whitened time-lagged coordinates. So these eigenvalues that again we are maximizing correspond to the time autocorrelations of the individual independent components or latent space vectors. So TICA finds a bunch of dimensions, latent space coordinates that are orthogonal in the whitened representation and whose time autocorrelations are maximal. So it finds the directions in which the data are slowest or the events are most rare. Okay, so in this way we have made the connection between minimizing the prediction error in time and maximizing the time autocorrelation or the slowness in time. For TCCA, so in the non-reversible, non-detailed balance case, we do not have such a simple interpretation in terms of autocorrelation because we find 2 sets of vectors that are maximally correlated in time, but the notion is similar as for TICA. So equipped with the equivalence between minimizing the time prediction error and maximizing a variational score, such as either the time autocorrelation or this time cross-correlation that we maximize in TCCA. We can now do something similar as we did when we derived time autoencoders and use this new score that we are maximizing in order to derive a neural network that finds a low-dimensional latent space embedding describing the slow motions or rare events. And because the score that we are maximizing operates only on the latent space and not on the full dimensional input or output spaces, we have a great advantage here. So we can define networks that map from input xt to the latent space. And this map can be called zt, but now we will just call it chi0 of xt because we will have possibly two different functions. And the second function, that's another neural network that will map xt plus tau to its latent space representation. So we have this pair of inputs xt and xt plus tau, and the pair of network outputs in latent space chi0 of xt and chi1 of xt plus tau. So, and these are now the latent space vectors, and we compute this score that we here call VAMP score. And there is a background story why this is called VAMP. VAMP means variational approach for Markov processes, and this has something to do with the fact that we find by maximizing the score also a best approximation to the singular functions of a Markov operator. But this is a more complicated story that I'm not going to tell in this lecture. But if we choose a VAMP1, so that is the trace norm instead of the Frobenius norm of this matrix that you see here, then this is just identical to canonical covariance analysis. So to do canonical covariance analysis in the latent space of these networks. Okay, but here we propose to maximize the VAMP2 score, so that is the Frobenius norm, and this is identical in the linear case. So if you do TCCA, you will not see any difference if you maximize the one or the two norms, or the trace norm or the Frobenius norm of this matrix. But for a neural network, it can make a difference, especially in terms of efficiency of the optimization. Now the C matrices here are simply the covariance matrix of the neural network outputs. So we compute them batch-wise. We pass a batch of xt's, xt plus 1s, etc. through the neural network lobes. We compute the latent space representations, and then for every batch we compute the covariance matrix of that batch. The operations shown here could be poorly numerically conditioned, so especially taking the inverse of matrices C00 and C11 that are computed from small batches could be problematic, because there might be eigenvalues that are identical or close to 0, and therefore we have a problem when inverting these matrices. And the natural way to solve this is to replace the direct estimators of C00 and C11 here by a shrinkage estimator. So to add to this result here just the sum of chi0 of xt times chi0 transposed of xt, to add to this a small multiple of the identity matrix, and the same for C11. But in practice, because we are operating in the latent space, we usually are working on low-dimensional vectors here. So practically, this is usually not a problem, and we can get away with no or very little regularization at this point. Okay, so this structure is called a VAMPnet, and the great advantage of something like a with respect to something like a time autoencoder is that we only use encoders here. Yeah, so we only have encoder networks that go from high-dimensional space to low-dimensional space. And this is something that is relatively easy to train, where we can go deep, where we can be quite efficient. Decoding or generating high-dimensional states from low-dimensional latent spaces is always more difficult, and training such networks, such decoder networks, is always more difficult. But it's also important to understand that this trick only works with a variational score, such as this VAMP score here, where we are maximizing this property. This would not work with the time reconstruction error. Yeah, it's important to understand the time reconstruction error makes sense on the input space, on xt and xt plus tau. I can encode xt to a latent space vector, decode it to xt plus tau, and ask how well did I do in reconstructing xt plus tau. If I would use the same idea in the latent space, so map xt with a trainable encoder to, let's say, ct or chi0 of xt, and then I do the same with xt plus tau. I map it with a trainable encoder to chi1 of xt plus tau, so the time-lagged latent vector. And I would now try to minimize the prediction error between these two time-lagged latent vectors. This I can do by searching for the transition matrix, just a linear transition matrix which does that. And I optimize that over all the parameters of the transition matrix and over the network parameters. What do I get? Well, nothing interesting. The problem is that this minimization problem can be solved by completely trivial projections. So for example, if I just always project on constant functions, then I can easily make my time propagation error in the latent space 0. So just having a 0 reconstruction error in the latent space doesn't mean anything. It doesn't mean that I have learned anything useful about my original time series. Whereas this variational score, maximizing this variational score, will have a useful optimum. Okay, VAMPnets were introduced in this paper cited here, and neural network structure could be pretty much anything that is suitable for your system that you want to represent. So it could be just a dense neural network, it could be a convolutional neural network, it could be a graph convolutional neural network or something else, whatever suits the structure, the natural inherent structure and topology of the data set that is of interest. So at the end of this lecture, I want to show you a few results of a VAMPnet analysis on a molecular dynamics trajectory. So in the top left, you see a small molecule that is called alanine dipeptide. It is a simple benchmark system that is often used to benchmark algorithms to analyze dynamics or the existence of different states in molecules. And it's something that we can easily simulate in a computer long enough so that we see all the relevant states. Usually what we simulate is not only this molecule, but is this molecule in a periodic box of water molecules. So we may simulate something like 1,000 or 2,000 atoms, but this is still easy to do for a long time scale. And if we simulate this for a very long time, we can do some statistics. So for example, we can do a histogram of where the values of these two torsion angles shown here, phi and psi, are. And these are the main or the most interesting degrees of freedom in the system. So the two parts of the molecule, the left and right part of the molecule, can rotate around these angles, the phi and the psi angles. There are also other rotation angles here. For example, at these end groups, these so-called CH3 groups, so those are these triangles spanned by the blue and the white balls. But these are less interesting because these groups are rotationally symmetric. But these phi and psi rotations, they are more interesting. So the distribution that I will get in a molecular dynamics simulation of phi and psi will depend, of course, on the molecular model used. But for common molecular models, I often get something like you see in the lower left of the picture. So you get something like 6 clusters or 6 states where the main transition or the slowest transition is between the 4 states on the left and the 2 states on the right. And then you also have slow but less slow transitions between up and down, so in the size space. And then you have faster transitions between the very left and the less left states of the phi variable. So what we did here was to take the molecular dynamics simulation of this molecule to evaluate it in the Cartesian coordinates, so the x, y, z coordinates of all the heavy atoms. So heavy atoms is everything that is not shown in white up on top here. So all the cyan, blue, and red atoms, carbons, nitrogens, oxygens. Use that as an input to the VAMPnet and train the VAMPnet to maximize the VAMP score, and have an output of 6 states, because we expect 6 long-lived states here. And the interesting result is that although the network has no direct information about angles or torsion angles, or that torsion angles are somehow important for this molecule, it learns a transformation of the Cartesian coordinates, or a nonlinear transformation, such that the torsion angles are effectively identified. So, and that is seen by the fact that the classifications of the 6 states that are just coming out of this unsupervised learning problem here are very clear in the phi psi plane. So in these angle coordinates, you get a clear clustering into the long-lived states, exactly where we expect them to be. So the network has effectively learned that angles are important and to cluster along these angles. Now, because these states are long-lived, they are well suited to build a so-called Markov state model. And that means, Markov state model means we discretize the state space into these 6 states. So basically we assign a discrete state to the system when it is in one of these 6 states, and then we compute a Markov chain transition matrix between these states in time. Yeah, so our latent space representation that we consider now is an assignment to these 6 states, or a classification into these 6 states. And how can we get that with a VAMPnet? Well, it's very straightforward with a VAMPnet, because we can simply define the last layer of each VAMPnet lobe to be a softmax layer. So we can just define the VAMPnet networks to perform a classification or a clustering by using a corresponding nonlinearity at the output, and then we automatically get a state assignment. And then the matrices that we will estimate as part of evaluating the loss of maximizing the VAMP score will actually directly give us a Markov chain transition matrix. So we immediately get a Markov state model by optimizing a VAMPnet without any additional computation. And this Markov state model is seen in panel D here. So you see 6 states. The size of these states correspond to the equilibrium probability. So if you run the chain for a long time, or you run the molecular dynamics simulation for a long time, how probable is it on average to be in either of these states? And state 1, 2, 3, 4 are quite probable. States 5 and 6 are quite improbable. In panel C here, you see the so-called relaxation timescales, or implied relaxation timescales of the system. So this is basically computing the eigenvalues of the transition matrix estimated at different lag times. So different lag times correspond to different VAMPnets, or maybe the same VAMPnet but different transition matrices estimated at these different lag times for a fixed set of encoder networks. And then we ask the question, the eigenvalues of these transition matrices, if we combine them with the lag time, so with the time unit at which this transition matrix was computed, we can compute a relaxation timescale. So we can ask the question, what is the relaxation timescale corresponding to this eigenvalue? And here we see that these timescales converge in tau. So if we make tau large enough, then the slow processes, the timescales of the slow processes can be reliably estimated. And that should be the case because these timescales are actually physical properties of the system. So they're invariant properties. They should not depend on which parameters you choose to make a model of the system. And then in panel E, what you see here is basically a test of the Markov state model. So this tests if the model that has been optimized to maximize this VAMP score, so to maximize these time correlations in the latent space, if this actually also achieves to minimize the propagation error. So in other words, if you take a Markov state model estimated at a certain lag time, and you make a prediction of the time series at longer lag times, and you compare with the data at these longer lag evaluated at these longer lag times, then you can see here that the agreement is very good within the statistical error, and so that means our model has successfully learned to propagate the long time dynamics of the system. Finally, we have because we have a loss function or a variational score that we optimize when we optimize VAMPnets, we can also use it to do hyperparameter optimization. So for example, we can ask the question, how many latent states do we want? Do we want 2, 3, 8, 6, etc.? And what we can do is we can simply compute the test set or the validation set error or the validation set VAMP score, and in this case maximize it over the number of states. And of course, if we use too few states, then we will somehow get underfitting. We will get a poor VAMP score. If we use too many, then at some point we will overfit and get also a reduction of the VAMP score. For this, of course, we have to define for how many dynamical processes we want to maximize the VAMP score. Okay, so with this, we are finished for the lecture. We have asked the question if we have a time series, so dynamical data, and we are interested in finding a manifold of that data that I assume to be high dimensional. We want to find a low-dimensional manifold which describes the slow processes or the rare events of that data. And we additionally make the assumption that we are somehow interested in Markovian models. So we are interested in the question if we look at times t and t plus tau, and tau defines what we mean by a long time, then we are interested to find representations of the data where the processes are slow compared to that time. Okay, so that was the content of this lecture, and we have found that there are linear and non-linear learning methods, so shallow and deep learning methods in order to achieve that. And there is a correspondence between these methods because we can define similar loss functions for both of them. We can on one hand say, give us a pair of an encoder and a decoder matrix, or an encoder and a decoder network, which minimizes the prediction error in time. On the other hand, we can say we define a variational score that measures slowness or time autocorrelation, and we optimize either linear matrix representations or neural networks with respect to that score. And all of this can be done, and it leads to different methods called time canonical covariance analysis, TICA, time-lagged independent component analysis, and the VAMPnet method. So much about Markovian methods. Thank you for your attention. Next lecture will be on recurrent neural networks.